Let's start the concept of standing waves. So now the most important categories of waves is we can categorize waves into traveling waves versus standing waves. So traveling waves transport energy from one area of space to another. And just have a look at these two animations. This is basically a transverse wave, which is transferring kinetic energy from left to right. Similarly, this is a longitudinal wave. The direction of the particle oscillation is different, but kinetic energy is being transferred from left to right, right? So transverse as well as longitudinal waves are a part of traveling waves only. So if any wave which can transport energy, primarily kinetic energy from one area of space to another, that is called the traveling wave. On the other hand, we have standing waves. The opposite of this is standing waves do not transport any sort of energy. So have a look at this animation. So these waves just go up and down in different loops. So you can see we have 4 loops here, and all the points are basically going up and down. Since the waves does not go side to side, either left or right, it cannot transport any energy. Hence the name standing wave. This is also called a stationary wave. All right. Now, the next concept is how are the standing waves produced? To answer that question, we need to understand two subtopics first, which are superposition of waves and reflection of the waves. Let's start with superposition first. Have a look at this animation. So in this case, we are having two wave pulses which are approaching each other and then they merge into one another. To explain this, watch this diagram. We have two wave pulses which are approaching each other. Now, at a particular point, both of them will merge. In this case, since both of the wave pulses are above the x-axis, they will add. This is what we call constructive interference, where the two wave pulses are added. And after that, the wave pulses proceed ahead. So B was coming from the left, it continues to the left. A was coming from the left-hand side and going to the right. After superposition, A continues towards the right-hand side. Now, this is what we call constructive interference or constructive superposition. The concept is amplitudes are added. Similarly, have a look at this second animation. Same thing, constructive interference, but the only difference is the wave pulses are moving below the x-axis. Although they are merging into one another, you can see amplitudes are getting added. That's why the name constructive. The exact opposite of this will be destructive. Let's see. Let's have a look at another animation. So watch this. Observe one pulse is above the x-axis, the other one is below the x-axis, and then when they merge, they subtract. So now have a look at this diagram. This is a descriptive analysis. Two wave pulses approaching each other, but one is above the x-axis, other one is below the x-axis. When they combine, they basically cancel each other out. Now, cancellation will only happen if A and B are having the same amplitudes. Same amplitudes, that's why when you subtract the two, it will become 0. And after that, wave pulses continue as it is. So the B continues to the left, A continues to the right. And that's what is happening in this particular diagram. And this is why amplitudes are getting subtracted and hence the name destructive interference. Now, so I want you to see another animation to analyze that particular point where the pulses cancel each other out. So if I play this animation and if I pause this, let's take it to that point. Watch this. When the two wave pulses approach each other and then when they merge, this is that exact point when the waves cancel each other out, and that is this particular diagram, right? And this is destructive interference. Good. Okay. Now, how are standing waves produced? Standing waves are produced if two traveling waves moving in opposite direction merge into one another. What were traveling waves? Traveling waves were those waves which go side to side, as in they can transfer kinetic energy. So if you have two traveling waves moving in the opposite direction and then they combine into one another, the result will be this kind of a wave which goes up and down. So have a look at this second animation. The black wave which you can see, that is the standing wave. But in the background, you can see two traveling waves. The bluish wave is traveling to the right hand side. The left is traveling to the, sorry, the red traveling wave is moving to the left hand side. And the result of it is this black wave, which is what we call as the standing wave or the stationary wave. All right, so now let's have a look at this animation. In this, you will be able to see one wave will come from the left-hand side, another wave will come from the right-hand side, and notice how they merge into one another to produce a standing wave. Watch this. Now, as you can see, the solid line is the standing wave. In the background, the dotted lines are the original traveling waves. Right, so the basic concept is you just need two traveling waves moving in opposite direction. And that's what creates the standing wave. All right. Now, in the real world, to get a standing wave, we should analyze one more topic. It's called the reflection of the waves. Then we will come to the point how are standing waves produced in the real world scenarios. Reflection of waves. Have a look at another animation. This is fairly self-explanatory. We have two wave pulses hitting a particular end. So we have basically a rod, and the rod is connected to a string, and the string has waves. The only difference over here, this particular end is fixed. As you can see, this point cannot move. On the other hand, the second point, this is movable. As you can see, this can go up and down. Right? So when a wave hits a fixed end, you can see it inverts. And when another wave hits a movable end, it doesn't invert. And that's what you need to remember. When the end is fixed, the wave inverts. When the end is free, it doesn't invert. But in both the cases, waves reflect, which means if the wave is coming from the left, it will go back to the left-hand side. That's reflection. The only difference is in one case it inverts, in another case it doesn't invert. Now, if we combine superposition with reflection, that's how we can analyze standing waves in a real world scenario. Let's see. Okay, just have a look at this video. In this case, we have two persons holding a particular string. Now, this person on the right-hand side will not let go of this particular end of the rope, which means this is a fixed end. This is not going to move. But on the left-hand side, this particular end, so the person will basically oscillate this particular left end. So this end will go up and down. Now, what's going to happen when the left person starts to give basic jerks to the left end, it will create wave pulses. So those wave pulses will go to the right hand side. And when they reach the extreme right end, as we just said, this person is holding this tail. So this is a fixed end. Whenever a wave pulse hits a fixed end, it reflects, but it inverts also. So the wave will invert and then they will travel back. Now, what will happen? Because of the continuous up and down motion on the left hand side, continuous wave pulses will produce, they will hit the fixed end, they will invert. So now observe, you will have two waves. One is coming from the left hand side, another reflected wave coming from the right. And when they merge into one another, you will see the standing wave. So let's play this video. Let's analyze. Now you can see the standing wave has taken shape. So basically you can see there are two loops. Now the two background traveling waves you cannot see. We just see the final result, superposition of two traveling waves. Now you can see these are two loops, right? So now this is on the left hand side. This is not the smallest standing wave possible. If you reduce the oscillation frequency of the left end, you will get the smallest possible standing wave. Now have a look at this small animation. This is having only one loop. So basically the string is just going up and down. This is the smallest possible standing wave because it is having only one loop. In the first video, it had two loops. Now, depending on the oscillation frequency, which means depending on the speed at which the left end is oscillating, you will have more and more number of loops. So let's have a look at this video. In this, there are 4 loops. That's the concept. You keep increasing the oscillation frequency, the number of loops will keep on increasing. All right, let's analyze this. We had, this is a standing wave in which you can see there are two loops. Now, if you can observe carefully, right in the middle, you have a point which doesn't move at all. That point is called a node. The definition is node is a point whose displacement is zero, which means the node point actually does not move at all. On the other hand, if you observe this particular point over here, this is vibrating with the maximum amplitude. These sort of points are called antinodes. And there are two antinodes in this particular situation because even this is vibrating up and down. What's the definition of antinodes? Those are the points whose displacement is maximum. And in other words, the antinode point moves with the maximum amplitude. Now for the exams, all you need to remember is what is a node, what is an antinode. Node will not move, antinode will vibrate with the maximum amplitude. All right, now this is the basic animation of a standing wave, but in the books and in the exams, of course, they will not show you the animation. In the exams, they represent standing waves like this. So the up and down motion is represented like this. So the solid line and the dotted line. So any point is just going up and down. So the points over here, so this particular point where my cursor is, this is a node which is not going to move. Even in this animation, you can see there are 1, 2, 3, 4, 5 nodes, 5 points which are not moving. And there are 1, 2, 3, and 4 points which are antinodes, which means vibrating with the maximum amplitude. So if you analyze this diagram, we have a node 1 over here. Let me write that, N1. Let's say N1 is the first node, N2 is the second node, N3 is the third antinode. And if you observe this particular point, which is vibrating with the maximum amplitude, this will be your antinode. Let's write antinode 1, and another point over here will be antinode 2, another will be antinode 3, and that's how you identify which is a node, which is an antinode. Now, for the exams, it's important for you to know what is the distance between any two adjacent nodes or distance between any two adjacent antinodes. So the logic is simple. If I draw a one particular cycle of a wave, we know the horizontal length of one cycle is called wavelength, lambda. So one full cycle corresponds to lambda. Right now, if you analyze this particular picture, if I start from node 1, go to node 2, and then to node 3, this is what completes one full cycle, which means the distance between the first node and the third antinode is lambda. So distance between node 1 and node 2 will be half of lambda, so lambda by 2. And that's the first important point which you need to remember for exams. Distance between consecutive nodes is lambda by 2. Similarly, distance between consecutive antinodes is also lambda by 2. Finally, distance between an adjacent node and an antinode will be lambda by 4. Why is that? Because as you can see, one antinode lies in between two nodes. That's why lambda by 4. Now for the exams, you just need to remember these three variations of distances.